Hello and welcome back to the part 3 of this tutorial. We implemented the clock, timer, GPIO peripherals so far and understood how radio communicates with the firmware. Now we start with writing our model for the radio peripheral. To save time, I have already included skeleton code for the radio module. So you can see it has a long list of MIO registers defined in a similar manner to the other peripherals. It also accepts callback functions which we will use to notify the emulator when radio device is enabled for receive or transmission. The handler for read operation is straightforward, exactly same as the timer, and we have also helper methods to return us the packet pointer register, which has significance due to the fact that we need this pointer to know the value of this pointer to copy packet content to the RAM location that firmware, the firmware radio interrupt handler will read from. Let's get back to the documentation. Exception return section. Exception return is the value loaded into LR register on exception entry. That's the magic value. The lowest 5 bits of this value provides information on the return stack and process. We also need to set these bits as well. Basically, this on a real CPU, loading this value into LR will trigger a mechanism called exception return sequence. This is what we will implement in that interrupt return function. Let's use one of the possible combination. We want to use MSB, non-floating, and return to thread mode. Let's use this one. Then set those 5 bits. This would be third bit, and 5th bit. And then I should write this. Now we are ready to jump to the IRQ handler, but before that let's also set the interrupt state register to the interrupt request number, and finally we put the value of that vector address to PC. So it should be handler address. And then also get the stack point. we use SP because it would point to the correct one. It will be selected correct there. Okay. The key method here is the write method, inside which we should handle task transmit enable and task receive enable commands from the firmware. Let's begin by just writing the address, simply setting the register value here. And then the tasks tx enable command. So when this event is raised by firmware, it wants to signal the radio that the firmware has copied the data into that RAM location. And if you recall from the previous video, the first byte of the packet structure in the RAM would be the length of the packet. So we read that length first at location pointed by packet, then convert it to int, and as an unsigned. Okay, and then we can read the payload itself. Size +1, including the, let's read it, yeah, including the length itself. Okay. Okay. Finally, we invoke the callback function, the emulator's callback function, if it is available. Alright, similarly for tasks RX enable, here we just need to invoke the callbacks, the callback. Okay, that's it. Also, we have a function here called setPacket, which will later we will use from emulator to simulate packet being received by radio. So basically, firmware, the emulator will call this function with some packet content, and that content will be copied to the packet PTR location. That's all. Now let's send some packets to the radio from the emulator and see what happens. I've already added these callbacks and set them up here. Then we need to figure out where to invoke the setPacket method. The ideal place obviously would be inside RX callback when the radio is ready for packet reception. But before that, let's look into the source code to gain better understanding of the ideal location. Okay, this is the main entry point of the firmware, and here is the forever loop. So at this stage, the firmware is all set up and should be able to receive packets correctly. So it seems that inside this function would be the ideal place to inject our packet. Let's find the address of this function. Now it's already here. So inside radio test base listen, we have a while loop. After the listening, it tries to, the while loop actually is a for loop basically, yeah, for 10 buffers. It tries to copy received message, and the return value is checked. If perhaps it tries to figure out if the packet was valid. So it seems that right here, before this comparison would be the ideal place, because we would figure out the invalid packets as well. Okay, let's go back, and inside the code hook, the reference to remember before after we copy the packets, we should also raise an event. If you recall from the previous video, when a packet reception is completed, the radio raises events end event, basically writing value 1 in that register. So next time when the firmware reads this register, it will know that this event is raised. Basically, packet is received completely. So let's do this. Set that register to get event end. The value should be 1. Then some packet as a binary. So remember, the first byte is length, so I'll send this and some random 2. Then we just call this set packet. Set packet, and you see. Okay, let's see what happens. Okay. Object is, oh, this is not, it's a function. Okay. we see that here or RX callback is invoked, and code which basically copies the packet is also called, but we see no response from the base node. Basically, the expected behavior here is that once a packet is received and it is a valid packet, then the base station, the base node, should reply with an announcement packet. So we don't see any log lines basically telling us, printing this line, radio packet transmit requested, because the announcement is an ongoing packet. So let's see why. Okay, inside the radio test base listen function, we have a call to listen start with a loop that tries to copy the received messages. So most probably if there is some operation to read the packet buffer, it should be here inside this function. Let's see the function graph. Seems to be a fairly simple function. It calls into CR listen, and CR listen doesn't seem to do anything with the packet PTR RAM location. Remember, it's where the packet is supposed to be, the received packet is supposed to be copied by radio. There's also get status, and nothing about that packet PTR. So, and this is kind of expectable, because if you remember, the radio peripheral is interrupt driven. It means that when a packet is received, processed, in response, the radio hardware raises interrupts, and not actually calling some sort of callback inside the firmware code. And the interrupts are being handled by what it called interrupt handler routines, and the list of interrupt handler routines is registered in the vector table. So in this case, the code that is going to be processing received packets would be registered here. As you can see, we have here vector number 44 hex is radio interrupt request handler. That's where the packet processing logic should exist, and you can see here in fact references to function pointer, packet begin function, PTR, and so on. Let's see the source code to speed it up. Radio IRQ handler. Okay. Function comment says radio interrupt handler. The radio interrupt handler is invoked exactly by hardware in response to certain radio events that are enabled to generate interrupts. And here the firmware author created this handler, which says, first off, it checks if the type of the event raised by radio is event's address. Remember, this is raised when a packet is being processed and only the address part is completed. For some reason, here the firmware calls this function, packet begin function pointer, passes this status, and the part that we are interested in is this: when the packet is completely received, meaning we have events end. In that case, the packet end function pointer is being called to process the packet data. So our emulator would also need to simulate interrupt request, so we can invoke this interrupt handler we just discovered. I strongly recommend reading the exception entry and return section of ARM Cortex-M architecture document to understand the interrupt handling well. Here I'm just highlighting the key parts. Exception handling: when the processor takes an exception, unless the exception is a tail chain or late arriving exception, the important about the processor pushes information onto the current stack. This operation is referred to stacking, and the structure of 8 data words is referred to as the stack frame. Okay, let's see. I've created this skeleton code for interrupt controller to speed it up the development. Here you see those 8 words. Context, I name it context register, and the order is important. Obviously, it starts with XPSR, PC, and down to R0. However, when using floating point routines, the Cortex-M processor automatically stacks the architecture floating point state as well. So this picture explains this in more detail. Here is the one we just saw, when you don't have floating point unit on your CPU, and this one is when FPU is enabled. I have both here as an array. Also, I defined 2 helper methods: save context and restore context, which basically pushes these register values to the current stack, as you can see here. If the floating point bit is set, then it uses the longer register list. If not, then the usual one. And the restore does the opposite. Okay. We're now ready to start writing two functions. One, interrupt inter. Basically, we will emulator will use to request an interrupt, and interrupt return, returning from the interrupt to the same instruction address that the firmware was executing before the interrupt occurred. At the interrupt entry, we need to read the get the interrupt handler address. So let's name it vector address. We have IRQ numbers, so we multiply that with 4, and then add the firmware base address to get us to that vector address. Then let's read the pointer using a unicorn engine. Vector address 4 byte, and then convert that to int. And then once we have this address, we also need one more piece of information to know which what's the current stack pointer, because we would have two stack pointers, master stack and master stack pointer and the process stack pointer. Also, we need to know if the CPU is in floating point mode or not. For this purpose, there is a special register called control register. We read that control register using Unicorn regret. Okay, and then let's see the documentation for this one. The special purpose control register is a 2 or 3 bit register, and bit number 1 defines the stack. So 0 is main stack pointer, 1 is current stack pointer. Also for FPU, if it is 0, it says that FPU is not active. Okay, so stack pointer select bit, let's read that bit, it would be the bit number 1, and then FP CA bit. Now we are ready to do the stacking, pushing those all context registers to the stack. We just call that helper function here, save context, pass it the which stack to use, and if the FPU is enabled. Once this is done, we're ready to invoke the RQ handler. However, before doing so, we need to put a magic value to the link register. When returning from the interrupt, we'll read the LR register that could contain the magic value. So use the mask. Then we read those bits. Space select. Insert bit. And let me see. Fifth bit. Now you're ready to restore the context. And now if we can let's read PC and SP as well. Also We also need to restore those bits in the control register. Second bit, okay. And finally, okay, we have an error here. We also need to handle the case when we don't have the magic value in LR. So in that case, we simply restore context using those control bits again. Let's ready to restore. Okay. Now we should get the PC. That's it. Let's take a quick look. Make sure there are no errors. Oops, yes. Should do this. Yes. Alright, let's go back to emulator and try our new interrupt handler to raise an interrupt here. Radio interrupt, if you recall, it was number 11 hex in the vector table, and we just see what's happening. Okay, nice. Here we got internal interrupt number 17, handler address 1CFF, and nice, neat. So here you see that radio packet transmit requested. So it means that our packet that we copied here actually is processed by the interrupt handler, and the firmware is sending a reply back, which has it contains of a length bit 3 and 004400, and that's exactly is this value that we sent in the request packet. Later on we will find out that this is actually a device ID. So the protocol, the Coriandolo protocol, is a simple one. It just sends the device ID as the first 3 bytes of the payload. So it seems that our interrupt enter function works correctly. However, as we didn't use the interrupt return, so we are not returning properly, and this causes this failure from Unicore. Let's implement that as well. Let's take a look at the RQ handler first. So you see, first instruction pushes these registers, the last one LR, and when interrupt is done, when returning, it pops these values. So basically the PC, when returning from radio RQ handler, the PC value will be set to LR, which would have some magic value starting with FF. That is not really a valid instruction address. So we would need to intercept this memory access and call interrupt return function, which will restore the PC here to the instruction just right before the interrupt, before when interrupt happened. That value should be, as you would expect, it should be this. Okay. Let's first define a mapping here, a special mapping. Let's say for exception return. It should let's start with this and the length of first as this. Let's see. Okay, and then we also need to define a hook. We define a code block hook here just to cover the whole range. Let's say mem block CV, and begin address of this one. And some random thing. Alt set. And then the hook itself. So here, let's get the IRQ number first. And before returning, let's also set a flag, a global flag, signaling or packet injector that we are returning from the interrupt. So if RQ number is in fact 17 or 11x. Then let's do radio interrupt return as true. Let's define this as and then we can call the interrupt return with 1 parameter, and then here finally inside that code access hook here, once we return from the interrupt, we again will hit this code, and if we just continue this path, the execution will be stuck here. So if we raise an interrupt once, at the following the interrupt we want to skip this block, so let's add something like this. Yes. And yeah. Set it to false. That does. Indicating that the radio interrupt is handled. Let's give it a try. Oops, we have here forgotten to do this. Okay, nice. It seems that interrupt return works as well. So we should see 9 such packet transmissions. Let's remove these memory access logs. See it more clearly. Okay. LEDs on, 5 seconds on, then LEDs off, and perfect. We see that once we send the packet, the firmware replies with the acknowledgement packet here, and also it blinks the LED. So when apparently when a packet is received, which is expected, the LED is set to hide, and then set to high, and then clear. And we also see the acknowledgement packet is being sent out, containing only 3 bytes. Let's go to documentation and verify these, see if this is the expected behavior. Inside the cr.c file, the protocol stack author has placed a brief documentation that reads as follows. messages transmitted by the sensor, yes, message transmitted by base. A message transmitted by sensor will always include the device identifier of the sensor. This is the part I skipped in our code. So basically the value you see here, we set, I left it as an exercise. You see that it starts with the lens and 3 bytes, 24-bit device ID. So this device ID, this must be the same value as provided to the code when the port call is enabled. It means that if this value you're injecting or sending to the firmware is not the same as the value defined here, let's see. Yeah. So you see that this constant defined here, sensor device ID is 004400. This should match the value we have defined. We are injecting in this packet. If not, then the code coverage would be incomplete, and more importantly, we won't receive the acknowledgement from the base stages. So a message transmitted by the base will include the device identifier of the sensor to which the message is targeted, and that's the reason we see this device ID here 00D44 and then 00. Since the base always transmits in response to the reception of a message from a sensor, the target of a base message is always to the sensor, initiating the message. Alright. The emulator is completed. You can extend this emulator to host other real-world custom radio stacks built on top of nRF52, nRF51, and also integrate a fuzzer to it. Please let me know your feedback and suggestions for the future content in the comment section, and thank you very much for watching this tutorial, and I hope you enjoyed it.